All right, today we want to look at the Green's theorem. The Green's theorem is another way to try and evaluate a line integral. When we have the line integral in the form, the integral of the curve, m dx plus n dy, one of the forms that we have in our, when we're looking at it from a, from a function form of it. If the region is simple connected region, piecewise smooth boundary, oriented counterclockwise, that is, the curve is transversed once so that the region always lies to the left. If m and n are continuous first partial derivatives in an open region containing R, then this line integral can be evaluated with this double integral of the region of the partial derivative of n, which is the y component, dx, minus the partial derivative of m, that's the x component, dy, dA. So the conditions for Green is a closed region oriented in a counterclockwise way. Oriented in a counterclockwise way. When we have that kind of an orientation, a closed curve oriented counterclockwise, the Green theorem applies. And this partial derivative of n in relationship to x, this partial derivative of m in relationship to y, we looked at when we looked at conservative vector fields. When they were the same, the vector field was conservative, and we'll come back and look at what that is. But that's the Green's theorem, just another way of evaluating a line integral. So if you have, and again, in some books, they use the integral sign with the circle there to show that it is oriented counterclockwise, that it's closed. So when you have that situation, here we go. A function dx plus a function dy on a curve. And the curve is the curve starting at 0, 0 on the path y equals x cubed to 1, 1, and then on the path y equals x back to 0, 0. So it is closed. It is counterclockwise oriented. Therefore, we can use the Green's theorem. Green's theorem pretty simply. Take the y component in relationship to x. You get 3x squared plus 3y squared. And if you take the component of y, the dx piece in relation to y, you get 3y squared. So you end up with 3x squared dy dx, whichever order you want to do it in it. But since it's oriented nicely in a vertical way, going from the bottom curve, x cubed, to the top curve, x, so that's y, and x is going from 0 to 1, and so we can evaluate this integral. And so this line integral equals 1/4. That's using the Green's theorem. That's using the Green's theorem. Now, where the Green theorem really comes out to help us out is if I have a conservative vector field. Remember, conservative vector field said it didn't matter what the path was. So here's a path oriented counterclockwise, and it is closed. Therefore, the integral of y cubed dx plus 3xy squared dy, because the derivative of the y component in relationship to x is 3y squared, dy, the partial derivative of y in relation to x, and the derivative of the x component in relation to y is going to be 3y squared. And so we end up with these. This is a conservative vector field because the derivative relationship to x of here is 3y squared. Derivative of m in relationship to y is 3y squared. That's equal to 0. And so even though I don't know what this curve is, I can't write this curve in some nice way. I don't know what it is. But because it is closed, counterclockwise oriented, the Green's theorem tells me that this is the result. If there's conservative vector field, these are always the same. So a closed curve of a conservative vector field is always 0. It's always 0. Okay? So that is the relationship of vector fields and closed curves. Another theorem related to that is the area. If R is a plane region bounded by a piecewise smooth closed curve, oriented counterclockwise, then the area of the region, okay, the infield, okay, the area of this region, can be found in a variety of ways, but here's one way. Okay, we can find it using a line integral, which is 1/2 the integral of the curve x dy minus y dx. Because this is the closed curve, I can use the Green's theorem to evaluate this, and I have the solution. I have the solution. Use a line integral to find the area of an ellipse. Here's an ellipse. X squared over a squared plus y squared over b squared equals 1. Okay? We oriented the ellipse in a counterclockwise way. What is this area? Now, if you go to the back of the book, you can find the area of it, and the area is pi a times b. But why? Because we can prove it. Because it is a closed, oriented, counterclockwise curve, this area of this infield, the area of the ellipse, is 1/2 the integral of the curve x dy minus y dx. Because it's a closed curve, right, I can use the Green's theorem to do it, or I could use what we've already know, because this is circular in a way, and we know that x is a cosine of the angle, and y is b cosine of the angle. X is a cosine t. dy, the dy would be b cosine t dt. Minus y, that would be b sine t. The dt, which would be minus a cosine t. So we have a times b cosine squared t, and then plus a times b sine squared t. ab is a constant, so we can bring it out. So we've got ab, already had the half over there. Cosine squared t plus sine squared t, which is 1. We're going all the way around, so it's going from 0 to 2 pi. So this is going to be 2 pi ab over 2, which is pi ab, which is the relationship of the area of an ellipse. So we just proved the area of ellipse formula using this area formula. Right? The Green's theorem, right, can be extended to a region with a hole in it. So here is the outside, which is the ellipse, and the inside. Now you gotta be oriented opposite ways to do that. So here's the line integral, 2xy dx plus x squared plus 2x dy. And the curve, c1 plus c2 is the boundary. So the derivative of this, since it's closed, the derivative of this is going to be in relationship to x, 2x plus 2. The derivative of this related to y is going to be 2x. So we take those two, subtract, we get 2 dA. So I can bring the 2 out. And so it's going to be 2 times the area of the region. Because that's what the area formula is, back from earlier work. The double integral of the region dA is the area. So this is going to be the area of the region. Well, the area of the region is the area of the ellipse, which we already found out with pi times AB, minus the area of the circle, which is pi r squared. Okay. The area of the circle is 1. A and B are 3 and 2. And so we just found the area of that region. Found the area of that region using the Green's theorem. So one last piece of this is an alternate form of the Green's theorem using with work. So here's our work formula. Integral of the curve f dot n ds, right? Where we have a f is minj, and if we have a path x of si plus y of sj. Take the derivative, right? And looking at it, okay, so using t and then finding n. Remember, t was the derivative of the I component plus the derivative of the j component, and n then is the reverse of those. So this was at a point, there would be t right and up, therefore n would be left and up. So we would end up with n. So now we can take the dot product, do the arithmetic, and we end up here, which is an alternate form of the Green's theorem, but work can be found by taking the double integral of the region if our curve is closed counterclockwise oriented. Then the divergence of f dA, back to the first section, we talked about the divergence of f. We didn't use it, but here we are using it, dA. Okay? Extension of this to 3 dimensions called the divergence theorem. We'll do that towards the end of the chapter. So there is what's the stuff dealing with the Green's